We're now going to talk about how to solve higher order differential equations. The most important ones when we're looking at are linear differential equations. There are other types of differential equations. We're going to look at how do we solve and deal with linear differential equations. As before, with first order differential equations, linear is the same idea. It just means that you have your derivatives, higher order derivatives, but you don't have a y times those derivatives. And your y term at the end is just y, not y squared or y cubed or any other power function of y. You have constants times each one of the derivative terms. Each one of those constants is a function of x only, and those can be nonlinear. It's mostly the linear part is the y. Your dependent variable needs to be linear. If you subject them to initial conditions, then you have an initial value problem. Notice that this is an nth order differential equation, and there's n minus 1 derivatives for your initial conditions. So you have y0, or y of x0, y prime of x0, all the way up to yn minus 1 of x0. So the nth minus 1 derivative will give you that values. We want to talk about when or not we have solutions. And so if your coefficients that can be functions of x are all continuous on I, and your very leading coefficient, a sub n of x, is not 0 for all x in that I, then if x0 is an element in I, then there exists a unique solution, y of x, to that initial value problem. In other words, if your initial condition has it to where all of these coefficients are continuous and your leading coefficient is not 0, then you have a unique solution. We also have such a thing called boundary value problems. Those are a little different. Boundary value problems are where, again, you're solving some differential equation. Let's look at a second order differential equation. So a second order differential equation will have a second derivative involved. And then they're subject to different conditions where you could have y of a equals y0 and y of b equals y1 or 2 or whatever you want to call it. In other words, we're not having them be the same x value as your initial condition. So, or you could have y prime of a equals, let's say, y1, and y prime of b equals y3. So you can, again, have different different conditions you're putting into this. The reason they're called boundary conditions, you think is a is one end and b is the other end. You can also have it where y of a is, let's say, another value, we'll call it y4, and y prime of b is another value we'll call y5. Or y prime of a equals y, another y, and y of b equals another y. So you can have different combinations of these. These are all the different combinations. A second order will have at most either y and y prime. It will not have a y double prime. So second order will only go up to y prime in those boundary conditions. If you want to determine if a solution exists for some y equals c1x squared plus c2x to the fourth plus 3 as a solution, we're going to look at this as being a solution to this differential equation, x squared y double prime minus 5xy prime plus 8y equals 24. We're going to start off with y of 0 equals 1 and y prime of 0 equals 3. So this is an initial value problem because we have the same x value in our y and our y prime. Notice with our second order differential equation, we went up to y prime in our initial conditions. When I look at this, I'm trying to decide, is there going to be a unique solution? And again, the thing to look at is, in your differential equation, are all of the coefficients, the x squared, the minus 5x, the 8, the 24, all of them continuous? And the answer is yes, they're all continuous. But the other thing is your leading coefficient, the one with the highest order, highest derivative, needs to be not 0. So when is x squared not 0? Well, x squared is not 0 when x is not 0. So x can't be 0, but this initial condition has y of 0 equals 1 and y prime of 0 equals 3. So therefore, there is no unique solution. Okay, let's look at another problem. Let's say in this case, y of -1 equals 0 and y of 1 equals 4. So this is a boundary value problem because we have different conditions for my x's. My independent variables are different values. So this is a boundary value problem. So the only way we find out if we have a unique solution here is to actually find out if we can get a solution to this. So we happen to know the solution to this differential equation. It's y equals c1 x squared plus c2 x to the fourth plus 3. We could prove that that is really a solution. So we should probably prove it as a solution before we do anything else with it. So again, we have y is equal to c1 x squared plus c2 x to the fourth plus 3. And so that was my solution. I want to prove it really is a solution. So one thing I notice is to prove something is a solution, you plug it in and see if you get the same thing. So we have y prime, y double prime, and y. So we have y. Let's find y prime. Y prime would be 2c1x plus 4c2x cubed, and y double prime would be 2c1 plus 12c2x squared. And so now the question is, does this actually satisfy the differential equation? So remember, my differential equation was x squared, y double prime, minus 5x y prime, plus 8y equals 24. So plugging those in, we're going to have x squared times 2c1 plus 12c2x squared minus 5x times 2c1x plus 4c2x cubed plus 8 times c1x squared plus c2x to the fourth plus 3. And we want to know if that equals 24. So multiply everything out, you get 2c1x squared plus 12c2x to the fourth minus 10c1x squared minus 20c2x to the fourth plus 8c1x squared plus 8c2x to the fourth plus 24, and we want to know if that equals 24. So hopefully all the x squareds and x terms, x to the fourth terms cancel out. So let's see, we have 2c1x squared minus 10c1x squared, which is minus 8c1x squared, and we have a plus 8c1x squared. So all the x squared terms just canceled. We have a 12c2x to the fourth minus 20c2x to the fourth, which is minus 8c2x to the fourth, and we have a plus 8c2x to the fourth. So those cancel. And then we left with 24 equals 24, which of course is true. 24 definitely equals 24. So that means so is a solution. Now the question is there a unique solution? So now what we must do is we must look at whether or not what our boundary conditions are. Remember, our boundary conditions in this case was y of -1 equals 0 and y of 1 equals 4. So we are using the y equation, not the y prime or y double prime, just the y equation. You're going to stick -1 in for x, you can stick 1 in for x. So y of -1 is going to equal c1 times -1 squared plus c2 times -1 to the fourth plus 3, and that's going to equal 0, because y of -1 was 0. And then the other one was y of 1, and y of 1 would be c1 y squared plus c2 y to the fourth plus 3, and that was going to equal 4. So I notice I have c1 plus c2 in the first equation equals -3 if I take that 3 to the side. And the second equation gives me c1 plus c2 equals 1 when I take the 3 to the other side. I notice I have 2 equations and 2 unknowns, so I get to solve this system. I think the easiest way to solve this system, you can do anything you want to solve this, but the easiest way I can see is multiply the second equation through by -1. And so we end up with C1 plus C2 equals -3, and negative C1 minus C2 equals -1. Adding those together, you get 0 equals -4. Well, 0 can't equal -4. So that means no solution. So the only way I can tell whether or not I have a unique solution is to actually find the solutions with those boundary conditions. In this case, those boundary conditions do not provide a solution. Let's try another example. Let's say we have y of -1 equals 0 and y of 1 equals 0. So again, we're only using y in this case. So we have y of -1 is c1 -1 squared plus c2 -1 to the 4th plus 3 equals 0. And the other one is c1 times 1 squared plus c2 times 1 to the 4th plus 3 equals 0. So I notice in this case I have c1 plus c2 equals -3, and c1 plus c2 equals -3. When I add those together, or subtract those, I should say, I'm going to get 0 equals 0. So that means, yeah, there's a solution, but it's not unique, because whenever we get 0 equals 0 in a system, we have infinitely many solutions. So there's no unique solution. Let's try one more. And that is y of 1 equals 3 and y of 2 equals 15. So again, we'll do y of 1, that's c1 y squared plus c2 y 1/4 plus 3 equals 3. And the other one is y of 2 is c1 times 2 squared plus c2 times 2 to the 4th plus 3 equals 15. So the first one I notice is c1 plus c2 equals 0. And the second one is 4c1 plus 16c2 equals 12. And again, I have a system of 2 equations and 2 unknowns. I need to solve that system. And again, I don't care how you do it. I notice if I multiply the first equation through by -4, and then I add them, I will have -4c1 minus 4c2 equals 0, and 4c1 plus 12c2, sorry, 16c2 equals 12. Add these together. I'm just ahead of myself because this is 12c2 equals 12. So c2 equals 1. And if c2 equals 1, going back to the first equation, c1 plus 1 equals 0. So c1 equals -1. So we do, in fact, get a unique solution because there it is. And in fact, the unique solution in this case would be y is equal to x squared minus x to the 4th plus 3. So now we know we have a unique solution to this, and that's what you do for boundary value problems. The next thing I want to look at is what we would call this differential equation is actually called non-homogeneous because the g of x doesn't, if the g of x doesn't equal 0, it's non-homogeneous. If it's equal to 0, then we call it homogeneous. And we can actually let the g of x equal to 0, and then we call it an associated homogeneous equation. And the reason we can say that is because the whole left-hand side is exactly the same no matter what the g of x is. If we let the g of x be 0, we call it the associated homogeneous equation. Any different equation that has this same left-hand side equal to some g of x are all associated. This one is called associated homogeneous because it equals 0. We can have a little bit of notation a little differently here. Instead of using dy dx, we can use dy. D is known as the differential operator. So the second derivative of y can be d squared y. We can then talk about having a new thing called L, which is a of n of x times d to the nth plus a n minus 1 of x times d to the n minus 1, all the way down to a1xd plus a0x. This is known as the linear operator, and the linear operator operates on any, it's kind of, you can distribute it through like we do anything else. So if I have a linear operator on alpha f of x plus beta g of x, I can actually distribute that L through and do just like we would do with any kind of linear equation. That's why it's called a linear operator. We can therefore rewrite our differential equations, which are really long to write, as just L of y equals g of x. It's just a shortcut way of writing these, a way to just kind of help us with doing this. That's just some notation. Another idea is what is called the superposition principle. This is where we have y1, y2 through y sub k are solutions to the homogeneous nth order differential equation on I. Then y is actually c1 times y1 plus c2 times y2, all the way up to ck some yk. That means it's also a solution. So we can actually just combine these together, and these are where the constants come from. So if we happen to know that y1 equals e to the 4x and y2 equals e to the negative x are solutions to some differential equation, then y equals c1 e to the 4x plus c2 e to the negative x is also a solution. And this is very useful because we're going to be finding these individual y values, y solutions, and then we can combine them together to get our solution. Another definition, this whole chapter is just a bunch of ideas behind some things, just some notation we're using for this section. So F1, F2 through Fn is said to be linearly dependent on I if C1 times F plus C2 times F2 plus all the way through Cn times Fn equals 0, with these C1s not all 0. And what we mean by that is if there's some way I can combine these together, but get 0 when I combine them together, but not all the C's are 0, then they're called linearly dependent. If it's not true, if they don't do this, then they're called linearly independent. So that shouldn't just be an N, it should be if not. So if this is not true, then we call them linearly independent. And that's what we're going to be looking at, is how we talk about that and deal with that. There's lots of different ways to prove it's linearly independent. I'm going to show you a way we kind of think about this, but I do want to point out that this is not the way we actually do this. We actually use something called a Wronskian, but this is just to give you an idea of what this means. So I've got these three functions. F1 is cosine of 2x, F2 is 1, and F3 is cosine squared of x. And I want to know if they're linearly dependent. So what I want to know is if I take C1 times F1 plus C2 times F2 plus C3 times F3, will I get 0? So that really is the question we want to know. So we want to know if C1 times cosine of 2x plus C2 times 1 plus C3 times cosine squared of x equals 0. If they're linearly independent, it means that the only way this can equal 0 is if each one of the C's is 0. So now my question is it possible that it's not 0? If there's some other way we can do this, we can get 0 without them all being 0. And if you can, then they're linearly dependent. So let's look at this. We have trig functions. So what we want to think about is all of our trig identities. One trig identity that we have is the cosine of 2x is 2 times the cosine squared of x minus 1. There's lots of different ones for cosine of 2x, but this is one I'm going to try using and just see what happens. Plus C2 times 1 plus C3 times cosine squared of x. Now, granted, I have a cosine squared is 1 minus sine squared, but I want to keep in cosines because I've got a cosine and cosine. So we have 2C1 cosine squared of x minus C1 plus C2 plus C3 cosine squared of x equals 0. Well, what might be helpful here is to put the cosine squareds together. So I notice I have a 2C1 plus a C3 times cosine squared of x. And then I have a minus C1 plus C2, which are just constants, equals 0. So the question is there any way that these can actually equal 0 without all of them being 0? So can 2C1 plus C3 equal 0? That would make this term go away. And can minus C1 plus C2 equal 0? Are there values that can solve this and find out what these values are without having to have them all be zeros? That's really the question here. So looking at this, I can see that if I actually oops, I think I lost a negative sign somewhere. No, okay, I didn't. Is there some way I can let these all be some value that's not 0 and get them equal to 0? So in other words, is there any way I can have C1 be a value and 2 times it plus C3 would give me 0? Well, the simplest one is, what if I let C1 equal 1? Then I have 2 times 1 equals C3 plus C3 equals 0. So that would mean C3 would equal negative 2. Well, that seems right. That works okay. Because if I put 1 in here and negative 2 in here, I'll get 0. So now the question is, do they make this other equation 0? Or is there some way we can make this equation equal to 0? So if I'm letting C1 be 1, then I notice, oh, well, C2 would have to equal 1. So that means that there actually are some constants. And there's lots of other constants you could have picked, by the way. But there are some constants I could let C1, C2, and C3 be, where I will get 0 here in this equation, but not because of them all being 0. In fact, if you look at this and you put this in, if you put 1 in here for C1, we get 2 cosine squared minus 1 minus 2 plus C3 times cosine squared, which was negative 2. So we have 2 minus 2C, and that's going to equal 0. And I'm sorry, I did these wrong. Then we have minus 1 plus 1, that's 0. So we get 0 equals 0. And that means we don't have these all 0, which means they're not linearly independent. Now, this is a long process, and we just kind of guessed what we thought it was. So let's see if we can't find a better way to do this. And there is a better way. It's what's known as the Wronskian. And the Wronskian is actually where your first row are your function, your second row is your derivative, your third row would be your second derivative, all the way down to your n minus first derivative, if you happen to have n functions. This is a square matrix, so it's you have the same rows as columns. That's why you have to go down to the n minus first derivative to get to where you have n rows and n columns. This vertical lines here mean you're finding the determinant of this. So this is actually the determinant of that Wronskian is what you want to do, and find out what that value is. So there's a nice little theorem that tells us that if y1, y2, and y sub, let's say all the way to y sub n, are n solutions of the homogeneous linear nth order differential equation on some interval, the set of solutions is linearly independent if and only if the Wronskian is not 0 for every x and I. So actually, what this means is if the Wronskian is not 0, then we will in fact have a linearly independent. And that's the main thing we work with this. And when we deal with that, we also can then have a fundamental set of solutions. And this is a solution is linearly independent. If these solutions are linearly independent, then your general solution is y is c1 times y1 plus c2 times y2, all the way up to cn times yn. All right. So let's try a problem. Let's verify that y1, which is the cosh, the hyperbolic cosine of 2x, y2 is the hyperbolic sine or sinh of 2x, form a fundamental set of solutions to y double prime minus 4y equals 0, and then write the general solution. So there's actually a multiple steps to this problem. The first multiple step to this problem is that we need to actually show that these are in fact solutions to this differential equation. So the way, again, you show something is a solution is you plug it in. So let's start with y1 equals the hyperbolic cosine of 2x. I need to find out if it's a solution, I need to plug it into the differential equation. So I need to find y double prime. So first let's find y prime. The derivative of cosh happens to be sinh, and the derivative of 2x, of course, is 2. So we're using the chain rule here. So we have 2 times the sinh of 2x. Then we need the second derivative. The derivative of sinh happens to be cosh. So we'd have 4 times the cosh of 2x. And then we want to know if this is in fact a solution to this. So remember our differential equation is y double prime minus 4y equals 0. So plugging that in, we're going to get 4 cosh 2x minus 4 times the cosh of 2x. And does that equal 0? Well, you can see 0 equals 0. So it is a solution. Let's do the exact same thing with the other solution. y2 is the sinh of 2x. Again, the derivative of sinh is cosh. So we have 2 times the cosh of 2x because you're doing the chain rule there. And then the second derivative, the derivative of cosh, of course, is sinh. So it's 4 times the sinh of 2x. So again, plugging that in, we'll get y double prime minus 4y equals 0 is our differential equation. So we have 4 sinh of 2x minus 4 times the sinh of 2x. And does that equal 0? Well, you can see, of course, 0 equals 0. So again, it's a solution. Unfortunately, that's not the end. All we've done is show that they're solutions. Now we need to show if they are in fact a fundamental linearly dependent. So we need to do that part next, which is the Wronskian. It is the determinant of it doesn't matter which one goes first. So the cosh of 2x, the sinh of 2x, yeah. And then, so your first row is just your functions, what your solutions are. Your second row is their derivatives. So the derivative of cosh of 2x is 2 sinh of 2x. And the derivative of sinh of 2x is 2 cosh of 2x. This is there's only 2 solutions, so there should only be 1 derivative that we're doing here. So we have a square matrix. Then you have to find the determinant of this. Where the determinant is, you multiply these two. You go down the diagonals, basically. So you multiply these diagonals together. You multiply these diagonals together, and you subtract the first one minus the second one. So this would be 2 times the cosh squared of 2x minus 2 times the sinh squared of 2x. All right, so we have this. And then the question is, what is this equal to? So we've got to figure out what is this equal to. So one of the things we remind you is what is the cosh and sinh. So the cosh of x happens to be e to the x. Well, let's go to ax. So it's e to the ax plus e to the minus ax all over 2. And the sinh of ax is e to the ax minus e to the minus ax all over 2. And this is why we wrote these this way, is because we happen to see in a lot of different equations we're going to solve in the future this combination of e to an ax and e to the minus ax. And so it's nice just to write these as functions, better looking functions, just instead of all these e's. So this is why we use this. So the cosh of 2x would be e to the 2x plus e to the minus 2x over 2. And that's being squared, because it is the cosh squared. And then we're going to have minus 2 times the sinh, which is e to the 2x minus e to the minus 2x over 2. And that again is being squared. So then we have to multiply all this out and find out what we have. So let's go ahead and do that. So we're going to have 2 over 4. This would be e to the 4x plus 2e to the, well, just plus 2 because the e to the 2x times e to the minus 2x is just 1. And then plus e to the minus 4x. And then minus 2 over 4. And again, this would be e to the 4x minus 2 minus or plus e to the minus 4x when you square those out. And so then we're going to go ahead and start collecting some like terms. So one of the things I notice is I've got 1/2. And I'm just going to pull the 1/2 out. So we've got an e to the 4x minus e to the 4x, which is 0. We have a 2 minus a negative 2, which is 2, which is 4. And we have e to the minus 4x minus e to the minus 4x, which is, of course, 0. So we end up with 2. Well, 2 is not 0. So that means that they're linearly independent because the Wronskian is not 0. All right, perfect. So now we know that they're solutions. We know that they now form a fundamental set of solutions. And that fundamental set of solutions is the solution of cosh of 2x and sinh of 2x. And so what we end up with is we can now write our solution. Our solution would be C1 times the cosh of 2x plus C2 times the sinh of 2x. All right. And that's all there is to figuring these out, is finding this determinant. I would highly suggest you can use technology to find the determinants for 3x3s, so they're not so large. All right. One last thing I do want to mention is y sub p is known as the particular solution. It's the solution that satisfies the non-homogeneous equation. It is, however, free of constants. In other words, there will not be a C1 or C2 or anything like that in there. The general solution to the non-homogeneous equation is where we're going to have y is C1 y1 plus C2 y2 plus all the way to Cn yn plus y sub p. And these first pieces are known as the complementary solution. The second one is known as the particular solution. y1, y2 through yn is that fundamental set of solutions to the associated homogeneous equation. And we will be using this concept for finding these solutions for all homogeneous and non-homogeneous equations. All right, I would do another example. It's kind of the same idea. You would again prove that each one of these is a solution to this differential equation, and then show using the Wronskian, showing they're linearly independent, and then writing the solution. Okay, and I'm not going to do that example, but you can see how that works through. Okay, and that's just an introduction to second order differential equations.